Um, Good afternoon. My name is Faith, and I'm going to take you through the first part of my engineering doctorate project, which is more of a technological applied inclined more than research, where we are developing a data model, which is an ontology for exchange of test range verification data. So this is a case of the Netherlands where there is a lot going on in the industry or in the utility industry with the Dutch subsurface, which is becoming increasingly congested due to energy transition projects where grids and cables hit district networks and pipelines are being dug into and added into the subsurface. There is fiber rollout project and also increased housing new developments that are coming up, and this increases the spaghetti of cables and pipes underground. This also comes with its own damages thereabout, and the direct cost of damages comes to about 57 million euros, and also socioeconomic costs there of traffic disruption, utility outages, and even project delays. So with the damages, there's a reason behind it. Well, in the Netherlands, before excavation can take place, contractors are legally required to submit a request through a system, and then they receive registered utility maps from networks, and the network owners provide data which is expected positions, but sometimes it is not actually the actual positions on the ground. So this causes deviations. These deviations causes accidents to take place and damages to take place. Now, for contractors to avoid this, they dig trial trenches to deal with the uncertainty of the trenches there and the pipes and cables that are there. So during this process, they capture what they find, sometimes using surveying equipment that produces high 3D data, and then they register the findings individually. Every other contractor registers their own asset register. And then they export it in whatever proprietary format and backfill. So the process of this data, when company 1, company 2, or ABC stores their data, they store it in different formats and have to cause, if any other company is interested in the polygon area, they have to re-excavate again to rediscover the pipes and cables that are underground. So therefore, this is what we are trying to tackle. How can this information that is collected in different formats of CAD files, of PDF, to be semantic interoperable? And therefore, our objective is to design and develop a semantic data model for the 3D trial range observations. Currently, there exists a model for the utility industry in the Netherlands, but it is UML information model. So this is XML file-based, and therefore it means that it is static document delivery, and also offers, in terms of spatial data, it provides 2D information. So the data model that we are proposing is a web-based semantic data model, which of course is extensible through linked data and can has also referenceable identifiers, can be queried, as we will see later. And also the information that we get here is not only 2D, but also 3D to give us the actual and true representation of the subsurface. The methodology that we used here is design science, where we identify the problem, the semantic gaps, which also informed the competency questions that were developed for the ontology. And then from the treatment design, which we are going to discuss the output of the treatment design, which is the ontology. We developed the ontology and modeled it. And also now we have done a little bit of instantiation and querying as the project goes on. So one of the things that were also keen to ensure is that we align it with existing frameworks of the 2D XML file-based EMKL model of the Dutch utility network, and also the SIWA data model. So the output of this is an ontology model, which we are going to discuss. It's logical. Now, the logical model here begins with two layers that establish where and how field data originates. So the context of the project and also how field data from what is the purpose of the test trench that is dug, what are the ground conditions and who verified. And you will realize that these triples here are the ones that will form the extensible data model that we'll work on, where a test trench is always part of the project and the verification activity that confirms where the test trench was dug and who dug it, and so that it can be traceable. In the physical findings layer of the logical model, this is the core model here, where each test trench observation can have multiple, sorry, I'll just go back to that. Each test trench can have multiple observations here, and the triples, we also work in to make sure that any kind of observation that is made from the test trenches has its supporting data in terms of the point cloud, if in case it's point cloud data, it's PDF or it's photos, and also ensure that we have the observed position, which is the innovation that we are trying to bring into this project to ensure that we have the 3D observation. And then this system logic layer handles the optional relationship between what was found on the ground and what is expected from the database that already exists, where an observation can be matched to a registered data asset that is already registered. Then the model allows for deviation to be calculated if it's not allowed. Now, this is a case of a test trench that we were able to scan. And on the right, it's instantiated so that you can see. This was a water pipe that we were able to scan among other pipes. And this is how it disintegrates in the model, which is for the test trench, we modeled it as a trench geometry and represented this as a WKT literal, which is a standard serialization of geosparkle data to be able to differentiate between the test trench with its geometry, aside from the components that are inside the test trench. Here you can see all the literals that are filled to identify the X location, Y location, and also the Z location, including other characteristics that are inside this test range. But what about for observations that are made where a casing is observed and inside it has also other pipes in the case of fiber cables? So in this case, we also modeled this as an object property here and could not ignore what is inside. So this was the case of instances where the pipe is installed, the trench is dug, and installation is made right there and then. So this data can be collected right at the point of installation. Now, once the field data is instantiated into the ontology, it becomes queryable. And this is also another innovation from what exists right now in the Dutch utility industry, where the query can be able to identify along the type of the pipe, the observation that was made, the diameter, the materials, the property that is used, and even the depth of cover, as is seen here, where the 3D is rendered. Now, this is our own ontology, which we call it the UTT, or Universal Test Range Ontology Model. But in terms of the ontology, we are able to refer to existing data model that already exists and make sure that it refers to already what exists through RDFC also. And because the Dutch data model also, it makes reference to the European Inspire Utility Networks model. So this model for the test trenches is making inference to the European Utility Networks model, which can be added for interoperability. At this stage of the project, this is where we have reached in terms of instantiation. But for the project as it continues, we'll be able to add QUDT integration so that the measurement properties such as depth are in meters, the diameter millimeters are able to be machine readable. And because this is a technological project, we will be able to work with stakeholders and do validation workshops to assess the model fitness and be able to see how to connect the ontology with external spatial data sets such as built environment, street infrastructure through linked data, and enable cross-domain utility management. Thank you so much for your attention. I'm happy to take your questions.